All right, we're going to go through the rubber stopper debrief. This is also known as the lab sim that you guys did. Again, I've done this lab physically using swinging a rubber stopper around the room, but I found it's been kind of more beneficial to use the lab sim, which worked out a little bit better. So let's just go briefly through the force diagrams that you guys should have drawn for your rubber stop for the moving mass. So I call this a top-down view of the object. So you have your moving mass was there, and then you had a string that was pulling it again around in a circle. So if I were to kind of just look at it from the top-down view, if I put the mass was going this way, it would also be kind of pulling it in towards the center. And then this is the side view of what was going. This is our glass tube is right here. So again, you had this same tension force, but now viewed from the side, as we saw over here. The hanging mass that we have here is being pulled upward by this tension force. This glass tube is frictionless and just kind of acts sort of like a weird pulley that changes the direction of the force. And then you had your hanging mass, M sub H times G, and this was your stack of washers. I didn't spell that right. That's okay. But this part was in equilibrium. If that wasn't super obvious from the sim that we did or the demonstration that I did, that tension force up was going to be equal to the weight of those washers. And that's going to be important for the extension question that you're going to do for today. So let's talk about what you looked at in your graphing. So I asked you to graph the linear speed of the moving mass as a function of the radius. So V as a function of R. This linear speed was 2 pi r divided by the period. So again, that calculation should be there as part of your lab. And you hopefully saw something that looked a little side-opening parabola-ish. And if you didn't, go back and fix your lab and adjust it, put that appropriate graph in there. And then as a result, you would have had a velocity squared is what we would have done in units of centimeters per second, whole thing squared, versus the radius in centimeters, and now we would have gotten a linear relationship. So the linear regression equation for this line, my y-axis variable was the speed squared, and that was going to be equal to some numerical value, and hopefully everybody should have gotten a different number. The units on my change in y would be centimeters over seconds, whole thing squared, divided by the units on the radius, which was just centimeters, and then multiplied times r. So this would be our regression equation that you should have recorded as part of your lab with, of course, your appropriate numbers to support. So now the physical significance of the slope. So when we look at the slope, we look at two things. We look at what was constant in the lab, what did not change. And then secondly, we also might look at the units of the slope to give us some intuition. So let's simplify these units. So we have centimeters squared over seconds squared. Divided by centimeters is the same as multiplying it by 1 over centimeters. So that is the equivalent of what we have up here is this part here. Centimeters cancel, and I get centimeters per second squared is my units of my slope with some number in front of it times r, and that is equal to v squared. So this, hopefully, something that jumps out at you that has units of centimeters per second squared. And what we recognize this to be a unit of acceleration, but not just any kind of acceleration. This is what we call the centripetal acceleration. Centripetal acceleration. Ooh, can I spell? Acceleration. That's close enough. So remember, when we talked at the beginning of the unit, we talked about that the linear acceleration of an object is equal to that parallel component of that acceleration plus the perpendicular component. This one was the change in speed. It was this perpendicular component that was the change in direction. This perpendicular component is what we associate with and call now the centripetal acceleration, because this is the part where the force that's acting on it is only changing the direction. Let's go back and look at this tension force one more time. So let's come back. I'll switch colors up to here. Let's look over here at this tension force. Notice if this thing is moving in this counterclockwise direction, right at that moment in time, I'm going to have a velocity vector that is acting tangent to the curve. And then I have my tension force tension, that is acting centripetally. From our workbook page that we just did, we know when a force acts perpendicular to the velocity, it does nothing to change the speed of it at all. There's no component that is acting parallel or anti-parallel. So this whole term, when we're looking at uniform circular motion, is just going to be equal to 0. And when the only force acting on it is really acting perpendicular, then we only simply have a change in direction. So this is what we call uniform circular motion. So uniform meaning no change in speed, but circular motion meaning that it has a change in direction. So circular motion has both change in speed and change in direction, but the uniform circular motion is telling me a constant speed. So yes, you can be accelerating if you're still moving with a constant speed if you are changing your direction. So I'll finish it up. So those are kind of the big ideas from the lab, and as far as you should have gotten in your first post-lab discussion. So where we're going to go from here that you're going to work on is the next page, where you're going to do a derivation to get an experimental value for the mass. And if you kind of open up your lab sheets, you can kind of follow along with me. Experimental value for the mass of your stack of washers. So the lab sheet will take you through calculating your actual value for your stack. So you'll have a certain number of washers, which should be different for everyone's. And then you're going to multiply that times 10 grams. Be mindful that 1 kilogram is equal to 1,000 grams. So you'll have to do a little unit conversion at some point. So this will be the actual value, your number of washers 10 times 10 grams. And then you're going to use your graph to determine experimental value, and then you'll do a % error calculation for this. So how are we going to do this? We're going to start with a net force equation. So if we now have our centripetal acceleration, I'll use purple now here, okay? This was the equation we had. I'm just going to rewrite this and call it velocity squared is equal to the slope, which we're going to call the centripetal acceleration times the radius of the circle that it's moving in. I'm going to rewrite this equation to solve for my centripetal acceleration. And this is how you most commonly and will see your equation written on your equation sheet. This will solve for the magnitude of the centripetal acceleration. So the centripetal accel. And this was equal to the slope of your v squared versus r graph. All right. So we can get the magnitude of the centripetalization graphically from a velocity squared versus radius graph. So we also discovered, looking at our free body diagrams, that there's a force that causes that centripetal acceleration. In the case of our moving mass, it was that tension force that was constantly acting to pull the mass as it was moving in a circle to keep it moving in that circular path. So Newton's law still holds for all kinds of linear acceleration, but in the context of uniform circular motion, this acceleration is going to be the centripetal acceleration. This m will be the mass of the object that is moving around in a circle. So the m here, the m system, is the object in circular motion. So the stack of washers were not in circular motion, only the moving mass was. And then still just equal to this net force. And this net force is sometimes referred to as the centripetal force. And it is, again, only forces that are acting directly towards the center or directly away from the center. So those perpendicular forces that change direction. So the centripetal force here is the new name that this gets in the context of when we're only talking about a change in direction. So how does this apply to this actual value? We're going to set up a net force equation. So our mass is given as part of the sim. The centripetal acceleration is the slope of your graph. And then the tension force, the force tension, is your centripetal force. That was what was causing the mass to move in a circle. So now we want to get this in terms of the mass of the washer. This is when we look back to our free body diagram and look at the system when it's in equilibrium. So let's go back to here. If we look at this system right here, this went neither up nor down. So the sum of the forces in that vertical direction of the hanging mass were equal to 0. This is a y. So my tension force was equal to the mass of the washers times G. So if we make that substitution, back into this equation, we can now solve for the mass of the washers. And I will just offer you an extreme caution that 10 is equal to 9.8 newtons per kilogram. So make sure all of your units are in kilograms, meters, and seconds for this to work out. So with that information, there is kind of a guided prompt there for you to fill in the blanks that'll narrate the derivation and for you to make the calculation and do a percent error calculation. That's it.